Okay. So welcome. This is Medea Vilray here. I'm with USGBC in the Middle Atlantic New England region, specifically New Jersey. Thank you to our panelists today. Thank you to our SAME group, the New York City chapter. We have terrific panelists here. I'm just going to go right ahead. And the main thing I want to give you is our CEU info for today. This is being recorded. You probably got a little pop-up about that. This is our planning committee, plus a couple people, Mike Scarano, Joe Manis, Rebecca Bentley, and Monique Owens that aren't pictured here. And we are in our third year of doing this series. We have 4 lunch and learns coming this year, and our summit will be in October. And I'm going to put a link in the chat with our next session on, I think I have a slide for it coming up on March 8th, and you'll get the registration info for that. So this is our Middle Atlantic region, myself in the middle there, Monique Owens and Rebecca Bentley. And you can reach out to us if you have any USGBC questions or needs. And a little pitch for membership. I can go on and on about that. So just send me a chat or an email if you're interested in learning more. And these are our Middle Atlantic sponsors. And here is our AIA CEU info. If you gave us your AIA number, we will report this for you. If you don't know if you gave it to me, just send me an email and we can double check. So these are the required slides, but as I said, if you gave us your number, we'll report it for you. I'll remind you at the end as well. And then we also have GBCI credits for today. Same deal. If you gave me your GBCI number, we will self-report it. We will report it for you. And if you're not sure if you gave me the number, send me an email. We also are offering PDHs for today. You have to fill out the survey. I'll send the survey after the session today. And then that qualifies you for the PDHs. So, oh yeah. So this is a session we have coming up in 2 weeks. And then this is the session we have coming up next month. And we'll have more info on that on the website, and I'll put the links in the chat. And I think that's it for my slides. And then I'm going to turn it over to Joe Por Vecchio. And Joe, let me pull up your slides, okay?
Thank you, Medea.
Sure. Feel free to introduce yourself while I'm getting those.
Okay, my name is Joe Por Vecchio. I'm on the board for the New York City Post SAME and long-term USGBC member. And I'm proud to say I've worked with several of the panelists, and we have some interesting things to cover today. But I wanted to introduce our audience to a LEED certified building that has just been commissioned. And it's in the Syracuse University. It's the National Veterans Resource Center, which is an unprecedented commitment from the university. It has 115,000 square feet, classrooms, gallery, parade grounds. It's LEED certified. Next slide, please. It's a first of a kind facility, and it really emphasizes Syracuse University's in the forefront of the first university to have an ROTC, and has a lot of programs that are dedicated to advancing the military veterans community relations. And the next slide. It has lecture halls and 750-seat auditorium. And what's germane about this LEED certified building is that it uses carbon dioxide to regulate the large rooms for the air changes per hour based on the occupant density. So when more people come and occupy a lecture hall, the outside air and the air changes per hour are increased based on the carbon dioxide levels in the building. We've used this in the Annisfield School of Business in Ramapo College that Bill Amann helped me in the design and operation getting that building started. So with that, I'd like to turn over the presentation to our first speaker, Bill Amann.
Thank you, Joe. Thank you very much. Thanks for everybody for attending and for a whole bunch of people for coordinating this. So let me get my screen up here. All right, that look good?
Looks good.
Okay, great. So we're gonna focus on indoor air quality today, and post COVID-19 lessons learned. You'll see I have the word post in quotes there because I'll talk about that a little bit. So it's important that we learn lessons from this pandemic and be smart and apply basic principles and strategies. So I'm going to cover some of the basic principles and strategies. Not all of this is new, but it's still very germane. Then Charles Bertuch is going to talk about how to apply these principles with goal of being efficient about it. And then Colonel Dacunto is going to tell us about some energy modeling, some CFD analysis. I'm sorry, CFD analysis that they've done. That's pretty neat and far better than other ways of doing it. We just asked for a quote from one of the CFD programs. It's $17,000 a license. Colonel Dacunto's version is much less. So that's what's on tap for today. All right, here we go. So I said we are post-pandemic, and indeed the president has said we're post-pandemic. The executive orders will stand down next month. But I saw this article, this story go by from Johns Hopkins. Does not make me warm and fuzzy. Future pandemics are inevitable. So that's again a good reason to apply the lessons learned, and particularly pertinent is this little quote here at the bottom. How can we be better prepared? Well, we can be better prepared. So that's what we're going to talk about today. We're post-pandemic, except that COVID-19 is still the #3 leading cause of death in the United States. We are still averaging about 3,500 deaths per week. That's 500 people a day dying from COVID-19 as reported to the CDC. I guess to put that in perspective, that's 3 Boeing 737s crashing every day. So I think if 3 Boeing 737s were crashing every day, we would give pause and we'd say, maybe we should be better prepared for our travel or whatever. So how do we prepare ourselves for within our built infrastructure? Just a lovely reminder that when we did this presentation a couple of years ago, we were talking about SARS-CoV-2. We're now talking about Omicron, and as the CDC calls them, variants of interest. There are lots and lots of variants, and not all of them matter a whole lot, but variants of interest certainly do. And if you look at this image compared to this image, you'll note some similarities. This is influenza. There are, and you talk about mutations and variations. So, and I know very little about the science, the biology here, but to realize that there's 18 different subtypes and 11 different subtypes of 2 different types of influenza. So again, this is just a respiratory virus, not even talking about noroviruses and other things. So anything we can do to stop transmission, whether it's COVID or one of its variants or other viruses, all of the same rules seem to apply to all of them. when I I got tested for COVID, they said, "Do you want us to test you for RSV?" I'm like, "What's RSV?" So sure enough, this winter we had quite a bit of RSV going around, combined with the flu, combined with COVID, again straining our hospital systems. And RSV, if you know, is mainly dangerous for very young children and the elderly. Well, that's still a population we need to be concerned about. So, so what do we do about that? So we know that transmission of these viruses largely happens as aerosolized particles. We know that in order to infection to occur, it's a matter of the dispersion of those particles into the space and inhalation by the occupants of the space. There is some particle deposition on surfaces within the space. And there's been a lot, because of COVID, a lot more modeling done with computational fluid dynamics. Again, Colonel Dacunto is going to talk about later. The bottom line is here, we've got these micro droplets that stay in the air for a long time, particularly in closed spaces. And we need to, if you want your population to stay healthy, we've got to address that. Researchers in Germany did a lot of analysis and looked at the main factors that contribute to the risk of being infected. This is all relative to the number one being staying at home by yourself. So the factors they found that had the greatest impact were the occupant density. How many people are in the space? How far apart are they from each other? In other words, the inverse of social distancing. The ventilation rate with respect to outside air primarily, and the exposure time. The longer you're in the space, obviously the greater the risk. So ASHRAE has had this standard for ventilation for many years. We were working with the 2019, and in most places that's still the current code, if you will. It's been reissued. We'll talk about that in a little bit. It's reissued every 3 years. But ASHRAE sets the standard. It's the Society of Heating, Refrigeration, Air Conditioning Engineers. Also, the National Standards Institute is a cohort in that. It forms the basis for the International Mechanical Code, but it only becomes a code requirement if and when a city or state adopts it, or the authority having jurisdiction adopts it. So that varies a lot from state to state, and enforcement of this varies a lot from state to state and within the state. So there is a standard. It's the minimum that they've calculated to prevent transmission of disease, minimum ventilation rate. It's also a function of the respiratory rate of the people in that space. These numbers have not changed for many, many years. And I did check the 2022. These changes have not been updated. The values have not been updated. So depending on the type of space, the minimum ventilation rate is dictated by the CFM, cubic feet per minute of outside air per person in the space. Plus there is a minimum requirement for outdoor air based on the square footage, just the size of the space, and the occupant density of the space. These are the default values typically, but they are typically used for calculating the values. So you can see that in office space, someone sedentary, not a lot of respiration going on, the value's down at 5 CFM per person. But in a place like a gym where people are very active, higher metabolism and higher respiratory rates, they've got the value set at 20 CFM per person. So, so these are minimum requirements. They do have consequences though with respect to energy use. The more outside air you pump into a building, the more intense the energy use is going to be to precondition that air. Just a typical HVAC system. The outside air is used for dilution to prevent a buildup of contaminants. And as Joe pointed out earlier, carbon dioxide is a good indicator of the contaminant level. So that's why we use that as an easy thing to measure. But there's all sorts of things in here within the condition space, including viruses. So the mixed air is filtered. Charles is going to talk about that. And we're mainly interested in the breathing zone, which is considered to be from 3 inches to 72 inches above the floor. It's the area of the air that we're really concerned about being healthy. A lot of people get confused by some of the terms. So air change rates within a space are fairly simple. The room volume is easy enough to calculate in cubic feet. You could, of course, do all this in metric also, but I'm old school. The ventilation rate is referring to the outside air rate, not the total capacity of the air handling system. So the air changes per hour, the formula is here. You have to convert minutes per hour and feet per minute, et cetera, into the cubic feet to get you air changes per hour, or the reciprocal of that is minutes per air change. Those are the basics. And here's an example of a space, 1,000 square feet, 8-foot ceiling height, 8,000 cubic feet with 1,000 CFM, 20% outside air would give you 1.5 air changes per hour, or 40 minutes per air change, which is not great. But that's the methodology. So the Charles is also going to talk about filtration in detail, but I'm just going to give you some of the basics here since I had all these pretty virus pictures. So the filtration is, you can use an insect screen to stop, softballs, but we're talking about some very, very small particles, and the filter rating is very much a factor of the size of the particle that you're trying to collect. So virus particles are typically in the 50 to 140 nanometer range, and the respiratory particles that they attach to are in 5 micron to 10 micron range, typically. So when you look at filter efficiencies, the minimum efficiency report value, MERV, we really don't use just percentages as factors anymore. We use these MERV values according to the ASHRAE rating system. But you'll see that filters that pre-pandemic were very typical, MERV 7s, they don't have any measurable efficiency on the small micron ranges that we're interested in. Even MERV 11s, only 20% efficient in the smaller micron ranges. MERV 13s, much better, or at least filtering half of those size particles out. And then MERV 14, we're up making a significant difference in the level of efficiency. Again, Charles is going to speak to this more to the point. And the obvious solution is to let's just put MERV 14 filters in everything. Well, most of the existing legacy HVAC equipment out there can't necessarily handle it. Some can, some can't. As we add resistance to the airstream, the given output of a fan will diminish. And that's kind of defeating our purpose. We're looking to move more air, not less. So we use these formulas, which are called the fan laws, to calculate whether we can increase the fan speed to handle higher levels of filtration. That chart I showed you before on filtration is here. It is kind of graphically, and we talked about the higher MERV ratings, and then we get into HEPA filters, which are very efficient at very high levels, and there's different grades of HEPA filters also when you get into critical environments. So that's pretty much it. Want to point out this is presented by the U.S. Green Building Council, and oh, guess what? LEED certified green buildings are better buildings. Compliance with ASHRAE 62.1 is a prerequisite, whether you're code, whether it's code in your area, whether it's being enforced or not. If you're getting LEED certified, that's being checked and double checked. MERV 13 filters are pretty much standard for every LEED certified building. And LEED does provide an incentive to provide additional outside air above and beyond the code minimum of 30%. So LEED certified buildings are inherently healthier and less prone to virus transmission. So for our CEUs, we want to talk about the key takeaways from this part. We're going to do Q&A at the end, I believe. So what factors are used to determine the minimum acceptable ventilation rate? Hoping everybody has picked that up from the presentation. I'll give you the answer. It's the occupant density, the room size, and the activity level. The second question is, how do filter ratings matter in regard to control of infectious particles? Well, the answer is the effectiveness at smaller micron sizes, range 1, improves as the MERV level increases. All right. So that's what I wanted to touch on today. And I'm going to turn it over to Charles. Take it from there.
Thank you very much, Bill. Appreciate it. 1 second, folks. Just want to make sure we're on there. Whoops. Excuse me, guys. You may have noticed if you looked at the bottom of Bill's slides, this is basically sponsored by the USGBC, but also by the Society of American Military Engineers. I want to take this opportunity to, thank Colonels Dacunto, Wallen, along with any veterans on part of this, including Joe and Eric Bacchus from Clarkson. I want to just sincerely thank them for their service. Also want to put in a shameless plug, if you don't mind, for the New York State Green Building Conference, which is going to be held March 2nd and 3rd here in Syracuse. I believe this is our 20th year. And you can get more information at that at esf.edu. It's sponsored by SUNY School of Environmental Science and Forestry. I'm going to be speaking on energy efficient indoor air quality. My work has been focused specifically on basically what's the most energy efficient way to provide improved control of COVID viruses in the built environment. As a basis, I'm starting with the ASHRAE recommendations. I'm a member of ASHRAE, work on the society and regional level, and quite familiar with their working groups that put these together pretty much in a hurry back when the pandemic first hit back in 2021. They did update these through the fall, and then really they haven't done much since because I think they figured they had pretty much what they needed. These are not ASHRAE standards. They didn't go through the ANSI process. However, they did put position papers out, and these are the recommendations from that. So the first thing they say is bring in as much outdoor air as we can. As was mentioned before, outdoor air helps dilute contaminants in the space. That includes COVID viruses. Do a pre or post occupancy flush to run a lot of outside air through your building, either before or afterwards. Use a minimum of MERV 13 filters on any HVAC equipment. A couple things like eliminate demand control ventilation. That was what Joe had mentioned earlier, that something they had instituted at the Veterans Center here in Syracuse. It's fairly common in most modern buildings now. But the idea is, rather than, unfortunately, when there's people in the space, bringing outdoor air, when they're not, bringing less, ASHRAE recommended disabling that entirely and always bringing as much as you can. Make sure your energy recovery units aren't allowing bypass between the exhaust and the supply. And then finally, basically provide humidification year round. And as you may know, here in the Northeast, it's very difficult because we have very dry winters. Everything on this list is going to lead to greater energy use in buildings. And, you need to look at it from the standpoint of, okay, well, we have to do it for health and safety, but you should still be looking at it and say, okay, how can we still meet the goals of health and safety and using as less additional energy as possible? So when you look at measuring, maximizing outdoor air, this is the single greatest energy increase of all the recommendations we just talked about. It is much more expensive and from an energy standpoint to condition air that you're bringing from the outdoors than it is to condition air that you're recirculating through the space. Bill had meant to talk through how you calculated outdoor air volumes for the existing codes, but looking at that as kind of a minimum, the question is, okay, how do you get more outdoor air through your system? Most equipment has the capability to bring in more outdoor air than it was originally designed for, as long as it's not a peak condition day. So in heating mode here in upstate New York, you might have sized your coils based on a -4 degree outdoor air temperature, but in reality, you're only going to hit that temperature literally 1% of the hours of the heating season. So there's other hours of the year you'll have additional capacity in your coils. The same thing applies to summer as well. So the point is, from ASHRAE's point of view, you can't just step back and say, I can't do any improvements in my outdoor air because of the capacity of equipment. Most equipment does have the capacity. At maximizing outdoor air is a very low cost to implement. Usually it's just either a controls change or a mechanical change a setting and a linkage in your system. But again, you double the amount of outdoor air coming in, you're going to double the amount of energy used to condition that outdoor air. One thing to note is, it should seem obvious, but sometimes people kind of miss this point. This is really not applicable to make up air systems that are already bringing 100% outside air. Essentially, the understanding there is if you're bringing in that much outside air, you really don't need to overfilter it. You don't need to sterilize it. It's the air that you're trying to duplicate. So, in some conditions, like out by a railroad yard or in a highway or someplace where there's volcanic activity, it may be relevant to treat that air, but more often than not, it's not necessary. The main concept I'm going to try to talk about today is equivalent air changes per hour. So the basic recommendation is to provide at least 3 air changes per hour into a space. 5 being probably best practice. And this is air changes of outdoor air per hour. Now, and we're going to get into these in a minute, but assuming that you can meet your 3 air changes or 5 air changes per hour with a certain amount of outdoor air, you can actually reduce that by putting in additional measures such as improved filtration, other technologies such as UV, ultraviolet light, portable AC units, even increased filtration. There's a litany of them. And what they'll do is each one of those will contribute to the equivalent air changes per hour. And the point is not to just arbitrarily bring in, say, 5 air changes an hour of outdoor air, but bring in enough outdoor air with additional treatment so you can get to that equivalent 5 air changes per hour. What I have on the right side of the screen here is a table that comes from a tool that was actually put out by ASHRAE that will help you calculate the equivalent air changes per hour based on a given space and the filtration type, the amount of outdoor air you're starting with, the type of space it is, the size of the space, the quantities of outdoor air you're starting with, and then adding factors for additional filtration, infrared lights or additional control measures. I'm not going to go through this whole table for you, but if anybody's interested in it, you can probably Google it pretty easily. It's a outdoor air calculator, or contact me and I can direct you to the spreadsheet. I might give you a concrete example, and I apologize, I'm an engineer, this is how I do things. A concrete example of how equivalent air changes per hour are developed, and I'm going to use a simple example with the MERV 8 versus MERV 13 filters. If you look on the left side of the screen, you're going to see where we started out with a total of 1,000 CFM. This represents an air handling system. 400 CFM of outside air, 600 CFM of return air. And if you look at the volume of the space, it's this particular space is, it's 1,000 square feet, 8-foot ceiling. It's an 8,000 cubic foot room. 400 CFM is equivalent to 24,000 cubic feet per hour. You do the very simple math. That's 3 air changes per hour, and that's using MERV 8 filters, which, as we talked about before, really don't have much filtering efficiency when it comes to removal of COVID viruses. The screen on the right shows basically the same system, but with MERV 13 filters. So we're still starting out with 3 air changes per hour of outdoor air, that 400 CFM. But now by running all this air through a MERV 13 filter with 85%, and I kept this to keep the numbers simple. Basically, we've taken that 600 CFM of return air, and now it's equivalent to 510 CFM of outdoor air because we've removed 85% of those particles. You add that up, you look at it from the standpoint of your 24,000 cubic foot room, and now we're at 6.8 equivalent air changes per hour. This same process applies whether you're looking at additional filtration, UV lights in an air handling system that are going to destroy the virus particles as they come through the unit. Any additional types of filtration that you may have, and then you can even add this. Well, we'll get into the portable units in a minute. Portable air cleaners are very common. These have been deployed in the hundreds of thousands across the country. Basically, they're small units. The schools put them in as fast as they could build them. And essentially what they'll do is they'll draw air in from the room and they'll run it through typically a HEPA filter that's built into the unit, or some will come with UV lights and some have specially treated filters. But the idea is it sits in a corner or somewhere in the room, brings the air through and cleans it. No special electrical requirements, everybody's got an outlet. They're all rated at what's called the clean air delivery rate. And that essentially says this particular unit, regardless of how much air it's actually moving, will basically provide clean air at a certain CFM level, an equivalent CFM level. So you can now look at that clean air delivery, do the same calculation we did before, look at it times that's in cubic feet per minute, how many cubic feet per hour, you divide that by the room volume, and it'll give you the air changes per hour. Most of the units, and we looked at over 85 buildings in New York State as part of a NYSERDA program. In most cases, these units, based on the clean air delivery rate rating of the portable units, add about 2.6 air changes per hour equivalent to the room. The one caution that I need to tell people is this is all typically based on the rated capacity of these fans, of these units, and they all have fans with generally multi-settings. There has been a lot of evidence of these that have been, I'd say, turned off, fan settings lowered, because when they're in a classroom and you need enough of them to provide the right air changes per hour, it can cause noise that would be distracting to the teachers and students. And it's not unusual to have for these to have been turned off or turned down. As soon as you do that, you're no longer getting that same clean air delivery rate, and thus you're not getting the equivalent air changes per hour that you seek. Ultraviolet germicidal radiation, called UVGI, basically is lights that will either go in an air handling unit or a physical ductwork, and it can also be in units that are mounted in a room up near the ceiling. and basically they'll irradiate ceiling or high areas of the room called upper room UVGI with UV light. These could be installed fairly easy. They don't add any static pressure to units, or very mild, minimal. These have been actually around for decades. They were generally used on the wet side of cooling coils, and basically UV has been shown effective to remove films on biofilms on cooling coils, same way it works with pathogens. And by removing those biofilms, it increases the heat transfer of that cooling coil or heating coil, but generally the problems with cooling coils because they're wet. Well, by using these units, you could actually show a positive payback. Even though you have to add electricity for the lights, your cooling efficiency goes up. So it's been used for a long time for that. Now they're being applied to for COVID issues. And where it works in terms of COVID remediation and energy savings is, although generally, and I've been involved in installation of many of these, between 1/10 of a watt and 0.15 watts per CFM is about what a properly sized unit will utilize. The fact that you can at the same time reduce the amount of outdoor air, because as we talked about before with the filters, you're removing more COVID particles, that allows you to decrease the amount of outdoor air you're bringing into the space, and thus you have an energy savings. And that energy savings from the reduced ventilation will more than offset the additional electricity use of the UV. Although I'm talking about this last, this should always be done first. And this is retrocommitting. Since anything, and this is pretty much right down the line, that you're going to do to improve indoor air quality is going to result in an increase in energy, you should always start by reducing the amount of energy that you need. And retrocommissioning is a process, it's a methodical, documented process that looks at your current building operations, not the way the building was designed to operate, but the way it should be operating now, based on the fact, assuming it's a building wasn't built last year, that it's now able to, maybe you have less people, you have less lighting loads, there's lots of things that could impact how you want to operate. And retrocommissioning basically evaluates that operation and then essentially commissions the building to make sure that it's working like it should. That includes schedules and set points, looking at control sequences, looking for things that have failed, valves that failed, sensors that are no longer calibrated. Retrocommissioning is something that here in New York State, NYSERDA will pay for 50% of under the FlexTech program, and it will universally have less than a 2-year payback. It's again, this is, if you're thinking about doing things to improve your indoor air quality, you should always start by retrocommissioning. I do want to just cover very briefly some other technologies that are out there. Photocatalytic oxidation, basically they use a metal oxide activated particle. It's activated by UV, it absorbs on the surface. Needlepoint bipolar ionization, many of these have been installed. This basically has an electric discharge, forms free ions. Those ions will either incapacitate or pathogens, or cause them to kind of clump together so they fall out. The problems generally, although they can be on a surface, they're not going to survive long on a surface. You'd rather have your viruses fall to the surface so they can be cleaned, or they'll sit there for a couple of days and float around where they're going to go into people's breathing zones. There has been independent testing on these that shows that they are effective, and they, again, as long as they're not producing ozone, which some of the older models did, they're safe. But as of today, they're not endorsed by the New York State Department of Education, ASHRAE, or the CDC. There are ozone generators that have been purported for use for COVID remediation. They should never be used in occupied spaces. Vaporized hydrogen peroxide, same thing. It's just not fit for human consumption. There's other wavelengths of UV that do work, but they're not as effective as UVC, and that's UVC is UV in the wavelengths that we use for UVGI, and there's a number of them. But I guess the point is, buyer beware. If you are interested in using technologies thoroughly research that particular technology along with other alternatives, because what you want to do is, you know, some things sound great, but you want to be able to look at them and really make sure that they work. There's been peer-reviewed testing, not just independent testing, but peer-reviewed testing, and that you know, if something works, you will see it, maybe not endorsed, but at least accepted by the main regulating agencies such as ASHRAE, New York State Education Department, or the CDC. And you want to try to you know, stick to that. I've got some very quick assessment of learning questions. Minimum desired equivalent air changes per hour to help spread the reduce the spread of viruses. And that's, you want to maintain a minimum of 3 equivalent air changes an hour, but you like to get up to 5. Common ways of improving equivalent air changes per hour: bring in more outdoor air, improve your filtration, use portable air cleaners or UVGI. And what is the first step that should be taken to minimize building energy use before implementing COVID control measures? And that's retrocommissioning. So I want to thank you all for your time, and certainly I guess at the end of the presentations, we'll be open for questions. Thank you.
So next up is Colonel Dacunto. Please take it from here.
Great. Good afternoon. Thanks to Charlie and Bill. I'm Colonel Phil De Kuntu. I'm an associate professor of environmental engineering here at the United States Military Academy. And I'd like to introduce you to some of the work my colleagues and I have done here on classroom aerosol dispersion. So I'll start by sharing my screen here. Okay. So the motivation for this was derived from our desire to investigate the safest ways to conduct in-person classes during the COVID-19 pandemic, though I think there's some interesting generalities that can be extracted from our results. So specifically, I'm going to first introduce you to some of our experimental efforts in classrooms and then discuss computational fluid dynamics modeling of some of the same rooms. And you see our 2 terminal learning objectives listed here. So we know that maintaining healthy indoor air is important in minimizing the spread of viruses. We also know that maintaining adequate ventilation is important in reducing exposure. However, so is understanding the dynamics of dispersion within the room. If the room is not perfectly well mixed, which it probably isn't, we can assume that locations closer to the source will have higher concentrations. This is known as the proximity effect. If you look at the photos below, you can see that if one stands within the visible plume of the cigarette or the person's breath as seen on a cold night, they will be exposed to higher concentrations of aerosol with corresponding increased exposure. In our case, we were particularly interested in the exposure of instructors who are typically in a higher risk category than students, especially cadets at the United States Military Academy. And finally, we wondered if the orientation of students with respect to HVAC supply and return mattered. So our research question was, what is the impact of classroom orientation and instructor location on instructor exposure to aerosols emitted from student desk locations? To answer this, we designed and executed a series of experiments that used a carbon dioxide tracer gas as a proxy for aerosols emitted from students. So you see here our experimental setup. We conducted a total of 20 different tests in 3 different university classrooms, each 35 to 55 minutes in duration, depending on the air exchange rate and the time needed to get to steady state conditions in the classroom. The photo here shows one of the 3 classrooms as an example. In the photo, you can see the 6 student desks with students represented by plastic silhouettes with a 100-watt light bulb to mimic the impact of the human form and heat plume on airflow. The carbon dioxide tracer gas was released from the mouth of each of our students via a half-inch tube at 1 meter per second exit velocity, which is a common exit velocity for breathing through the mouth, according to the literature. Our assumption was that the carbon dioxide tracer would follow the streamlines in a similar manner to the potentially infectious aerosols. There were a number of monitors arrayed throughout the room, with 12 around the periphery on survey tripods at 5-foot height to monitor likely instructor locations, and 1 at each student desk. In addition, there was 1 at the return. We conducted experiments separately with gas released in 2 different directions, 1 toward the return and 1 away from it. The 3 classrooms were arrayed as follows. Let's take a look at classroom number 2 in the upper right of the slide as an example. Here are the 6 desks with the silhouettes and carbon dioxide release. The red squares denote monitor locations. Blue squares show HVAC supply in the ceiling, and the square in the corner is the return. The 3 classrooms were somewhat similar in dimensions, though HVAC supply and return did vary. Classroom 1 had only 2 supplies in the center of the room, with a return into the hallway in the lower portion of the door, while classroom 3 had 6 rectangular supplies in the ceiling with a corresponding return in the corner, similar to classroom 2. We conducted experiments at a variety of air change rates as controlled by the ventilation system, with exact air change rates measured by separate carbon dioxide tracer decay experiments. Since steady state concentrations would vary by ventilation rate, we normalized them by the value at the return. In other words, concentrations higher than those at the return would be greater than 1.0, while those less than those at the return would be less than 1.0. We established 6 zones where instructors might stand with their nomenclature dependent upon their spatial relation with respect to the return. So for example, zone F in the upper right corner was always in the corner of where the return was, with zone C in the corner farthest from the return. The large arrows on this particular slide show the direction that the students are facing. The hypothesis was that perhaps it would be better to stand on the wall opposite the return for the instructor, with students facing away from the return, so that the aerosols would get swept up in the overall flow toward the return and thus away from the instructor. To aid in analysis, we established a parameter called CN zone, you see that at the bottom, which was the mean normalized concentration in each of the zones. In other words, the average of the normalized steady state concentration of the 3 monitors in each instructor zone. So what did we find? This plot depicts monitor responses in raw carbon dioxide concentrations on the y-axis over time on the x-axis in one of the 55-minute experiments. Those responses with wildly varying concentrations are those at the student desks that were in close proximity to the source locations. Those that form the more even plot of the step function that reaches steady state at about 800 parts per million are the ones on the periphery of the room in the instructor locations. We designed the length of the experiment so that based on the air change rate, the room would be at least 95% of the way to steady state during a 10-minute period at the end of the experiment. The one green line, just over 500 parts per million at the very bottom, shows a monitor in the adjacent room on the same air handling system, which we assume to be the background concentration of supply air entering the return. Results of our CN zone parameter calculations are as follows. Here you see the same graphic as before in the upper left for orientation purposes, along with 3 plots, 1 per classroom. Each plot shows CN zone on the y-axis by each zone on the X. Results are the average of all tests in a particular configuration. So for example, in classroom 1 in the upper right, you see the average of 4 tests toward the return and again 4 tests away from the return. Results vary by classroom, but I think you can see that there's a general pattern of higher concentrations on the edges in the A and F zones, which are closest to the return, with lower values in the middle in the C and D zones, which are farthest from the return. However, no clear pattern emerges for releases away versus toward the return. In 2 classrooms, orientation away from the return gives generally higher concentrations at instructor locations, but in 1 classroom, it's the opposite effect that's true, with much overlapping of the error bars. So in summary, combining results from all 3 classrooms, we get the following table. This shows the clear pattern of lower concentrations generally in the C and D zones, you see right in the middle of the table there, with highest in the F corner where the return is located. This effect is consistent regardless of classroom orientation, so we conclude that classroom orientation had no clear effect, at least in these experiments. In addition, we should note that all the instructor zones around the periphery of the room were much better than the sampling locations in the central desk area, which had a mean 2.9 times the concentration of the return up to a maximum of almost 10 times that of the return in 1 experiment. So this brings us to our CFD modeling work. Such modeling has the advantage of being able to test a wide variety of conditions easily and precisely, but it can be costly in terms of hardware, software, computational time, and operator training. Lower cost flow simulation tools exist. I know Bill alluded to this earlier in the panel. For example, there's one embedded within SolidWorks called FlowSim that is reasonably easy to learn and may already be available to many institutions. We wanted to know how useful a lower cost CFD tool such as this might be for modeling aerosol dispersion. So the objective of this part of the study was to assess the utility of such a low-cost FlowSim tool by comparing its results to the previous physical experiments that I just described. SolidWorks FlowSim is a CFD tool that is reasonably low cost and easy to learn. In addition, since SolidWorks is a fairly common design software, many institutions may already have access to this tool. FlowSim uses Favre average Navier-Stokes equations with a K-epsilon turbulence model. To employ it, we divided our modeled classroom. In this case, you see classroom 1 modeled at the bottom of the slide. We divided into a grid of over 500,000 cells with boundary conditions to mimic those of the actual physical experiments, as seen in the figure below. The model took into account the flow through the return in the lower portion of the door, the pressure differences measured under the door, the tracer gas emission rate and heat source from each of the 6 students, the heat flux through the windows, and the 3D inlet velocities from the supply vents, which you can see in the upper right of the figure, which could be obtained from a separate external flow study of the 4-way diffusers. So in the course of modeling classroom number 1, we conducted a sensitivity analysis of boundary conditions to determine which ones had the greatest impact on our results. This resulted in the completion of 10 total runs, as listed in the table on the left side of the slide. Runs 1 and 6 were the base cases at low and high flow with all boundary conditions included. On the right side of the slide, you see the criteria by which we evaluated model results, taken from a 2012 paper on dispersion model evaluation by authors Hannah and Chang. The 4 criteria are calculated by comparing C observed from the physical experiments to C predicted from the models at all measurement points within the room. In our case, this was the 12 extractor locations and the return vent. Values were calculated as averages from the last 10 minutes, or that steady state portion of the experiment that I talked about earlier. So we present a few results here. This slide shows concentration isosurfaces resulted from 2 runs in the low flow condition. The one on the left is from the low flow base case with all boundary conditions included, including the student heat sources. And on the right is the same experiment modeled without the student heat sources. So that was the one boundary condition removed. As you can see, there's a significant difference between the two. On the left, the tracer gas immediately rises toward the ceiling as a result of the thermal influence of the student heat sources, whereas on the right, the plumes immediately sink and head straight toward the return at the door. This table summarizes results from all monitors and the resultant dispersion model performance using the same evaluation criteria I talked about earlier. Along the top of the table, you see the 4 parameters, as well as the acceptance criteria for each. And down the left side are listed the 10 different runs with boundary conditions removed as indicated. In summary, the baseline SolidWorks models meet acceptance criteria by a long shot for classroom 1. Most of the subsequent runs with boundary conditions removed meet the criteria as well, with only one boundary condition having an influence great enough to cause the model results to fail to meet the acceptance criteria as the result of its removal. And so that was the student heat flux in the low flow conditions. Those 2 parameters are boxed in red as indicated. Some more results. So depicted here are results from modeling of another classroom, classroom number 2, which I present here to show the utility of modeling, even with a relatively simple program such as SolidWorks. The model of this classroom also met the acceptance criteria. On the left is the base case, in which all windows and doors were closed as they were in the experiment. Colors depicted the mass fraction concentration of carbon dioxide tracer gas. On the right, we show the same model, but with boundary conditions changed so that the rear door, there were 2 doors to this classroom, the rear door was opened and replaced by a static pressure differential. You can see how the single simple intervention, opening the door, drops the tracer gas and thus presumably the infectious aerosol concentrations dramatically throughout the room. We also modeled a single open window, and that's depicted here on the right. Here, the results are not as drastic from that just opening one window versus a door, but you can see the benefit for those students in the second row. So sit next to the window. In conclusion, our results indicate that SolidWorks FlowSim can be used to create reasonably accurate models of aerosol dispersion, despite its reasonably low cost. Since many academic institutions or other institutions may already have access to it, it may be a helpful first pass modeling tool for checking aerosol dispersion in a variety of conditions. We look forward to continuing some of this work by expanding the model to additional classrooms and classroom conditions, and also comparing results to a much more expensive modeling tool called STAR CCM. In addition, we have started work on a small scale physical model for visualization using a rhodamine dye in a water medium as pictured below. So thanks so much for your interest. That's my point of contact info, as well as a couple of papers that you might be interested in. Here again are the terminal learning objectives. So the first one, explain an experimental method for investigating aerosol dispersion in some classrooms and describe results from one set of experiments. Well, you could, as we did, release CO2 tracer gas into a room with an array of monitors, put them around the periphery of the room, away from, and when you do that, found that away from the return had the lowest exposure, as well as around the periphery of the room. And then we found that classroom orientation had no significant impact. And the second learning objective, describe the advantages and disadvantages of CFD and the utility of SolidWorks FlowSim. So the advantages are that we can test a wide variety of conditions easily and precisely. Disadvantages are computational time, and it may or may not actually be accurate. But SolidWorks FlowSim worked pretty well in our case and met those dispersion model acceptance criteria, and thus shows some promise. So that's it. Thanks so much for your interest. And with that, I believe the panel is open for questions.
Thank you all.
very much.
Absolutely wonderful comments. If I can, Joe, I saw that in the chat, there was one question. And the question was from Hugh, who asked, is it worth increasing outdoor air by 30% to increase lead points if it reduces the ability to obtain energy efficiency points?
Well, I'm going to just throw out my answer, which is I always discourage buying points. You know, you should always, if you want to do a lead project, the reason why people do lead projects is to have a better building, and, do things that make sense. Don't do them just to, buy a point. So that's my perspective. But again, I welcome a response from somebody more closely associated with the USGBC.
I agree with Charles completely. You're looking at, each particular project. What are the goals of the project? Who are the intended occupants? It's a holistic system. Yes, there are trade-offs, and for any given project, there is not one set answer for that type of question. You need to look at it holistically. And if you're looking for a healthy building, I would encourage increasing the outside air and find other ways to reduce the energy use through the thermal envelope, through more efficient fans and fan motors. There's all sorts of tools to accomplish both. You don't have to give up one for the sake of the other.
No, thank you. And just for those, if anyone does have a question, please feel free to drop it in the chat. You do see other things, other upcoming events are being posted in the chat. I do have a question for Colonel De Kuntu, and that is, the research you did just looked absolutely amazing. And the question I have is that a research is like, I guess, what's the next phase of that research? What does it look like? How are cadets involved? Where is that being presented? I'm just curious about what that looks like.
Yeah, thanks, Ben. Right now, we're in the process of trying to, we collected a lot of experimental data, and so now we're in the modeling phase. So we've done a complete model, more or less, of Classroom 1 and Classroom 2. We need to expand that to Classroom 3 so we can get a holistic look to see how well overall does SolidWorks do. One of the challenges I think we have is that each individual room is unique, right? And so what I found in Classroom 1 may not even be applicable to the classroom next door. So what we're trying to do is establish some broad themes through the modeling as well as the experimental work. But the experimental work was a huge campaign, and it took a lot of effort. So we're going to try to finish up the modeling first before we embark on that in the future. But I've had a few different other faculty and cadets, and we've presented and at a couple conferences, and then also have this going out in papers. So it's been a great opportunity for both cadets and faculty to engage in this type of research. So thank you.
No, excellent. Thank you. And then really for the whole panel, one other question I had is, as we look at the continuing, I think, Bill, you made the point that, we're going to have something coming up in the future. We don't know what it's going to be, but we'll have something to deal with. And so there's the recommendation that we should have the 3 air exchanges, ideally up to 5. Are there best practices to convert from what current systems are to that, so it's not a full retrograde? Or is that, just as with our infrastructure, that we don't get a very good report card grade when we look at those, how's the US infrastructure doing? How do we fix that component? Or is there a way to do that better, easier?
So we find that it really varies on the, what type of space and what type of system you're dealing with. We've got schools with unit ventilators. They're not, there's no easy solution for those. We're taking some schools and abandoning or removing the unit ventilators and going to overhead systems with dedicated outdoor air systems to improve the ventilation. There's no set answers. I noticed in Colonel Dacunto's different models, you had the classroom with the conventional diffusers versus the slot diffusers. So, architects love the slot diffusers because they're less obvious on the ceiling, but they're not really good diffusers. The word diffuse, right? The old style diffusers with the cones create an induction effect that add to mixing in the space. Is that what you want? Well, I think I have to go back to the Colonel and say, well, let's model both of those and see how what we're trying to achieve. Ideally we'd be putting HEPA filters and going into laminar flow in all these spaces, but nobody can afford that. So there has to be a happy medium that's affordable, and it depends on what you're working with to start.
And I just want to add, along the lines of Colonel Vaughn's question about how you, or at least how I interpret the question, what's the best way to increase, your outdoor air? If the idea is to, I really want to, just bring in more air. Maybe it's not about equivalent air changes. Maybe it's about bringing in more air. I would take the time to, you or have a professional really understand your system, understand those system capabilities, how it's really operating. It's easy to say, oh, you can't do it. But when you start, particularly if you have any means of an advanced control system available, a building management system that can change the operations based on outdoor air conditions, occupancy, or how the system's actually operating, which is not all that complicated. There's things you can do. Again, it may not give you the maximum outdoor air at a design day, but it will allow you to maximize the amount of air you want to bring in, and most other times.
Thank you. And then we had a few more questions in the chat. One of them is directed towards Colonel De Kuntu, which is, for the classroom experiments, any comment on the number of returns or the separation between them?
Right. No, no comment on that. We that was one variable we didn't really test for. There was one. So They said number of returns. I'm wondering if they meant number of supplies, or it could be supplies or returns. But in each classroom we tested, there was only one return and either 4 or 2 supply. No, let's see, 4, 2, or actually they all had different numbers of supplies because one had the slot diffusers. And so we haven't gotten to that level of analysis yet. Again, it gets back to can be so many individual configurations of the classrooms. The other question is, where are the returns, right? Or where are the students seated with respect to the return? We found in some cases, if they were seated right behind a supply and the instructor was in front of it, that created sort of a barrier almost, so that the aerosols would not move forward, they would just move backward. So many different variables, but no comment on that at this point. We have to finish our classroom modeling of classroom 3 first, but that would be, just that shows the advantage of modeling as well. We can, once we know the models work pretty well for each classroom, and we think they do, we can very easily change those parameters and experiment with a large number of different variables. So great question, more to follow.
That's great. And then I have one more question before I turn it back over to Joe for any additional points or questions he has. There was a question of any thoughts about the Mitsubishi wall units?
I have an opinion. So love them, particularly the cold climate air source heat pump versions for heating and cooling. But in this country and mostly in this country, but elsewhere in the world, we put our H, our V, our A, and our C all together in one unit because it's cheap and easy. But that was a bad idea, and the Mitsubishi units don't lend themselves. They do the H and the C. They don't do the V, right? They heat and cool, but your ventilation really has to be from a separate system. I know some of them you can put a tiny little outside air duct into, but they have the efficiency of the filtration is minimal, and they're not really designed to ventilate or condition outside air. So you use them in tandem with dedicated outside air systems or other makeup air and exhaust. They're great. They're wonderful units, but they're good at certain things and not so much of others.
Excellent. Thank you. Joe, I'll turn it back over to you. A pleasure to be monitoring the chat and being here with you all.
Well, thank you so much, sir. That's great. I can't believe how great this presentation series went and how everyone complimented each other in terms of the technical data. It was just remarkable. I have two relatives, a niece and a daughter-in-law that are teachers in schools, and they are teaching in different buildings that are 40-year-old building stock. They have radiators and they have windows. So they said, gee, what do we do? How do we know whether or not we have the proper ventilation in the room? So what I told them is, well, why don't you get a low-cost carbon dioxide monitor and put it on your desk and look at it. And this one has the air is good, it is okay, or is poor. And if the needle moves to poor, open the window. So that's a quick solution for a problem of contaminated air that may be in a classroom for a 40-year-old building stock. The more modern buildings, they have a lot of difficulty. The facility operators that manage the building, they respond to complaints. So if they have complaints that a room is too cool or too hot, they adjust the airflow and compromise the design of the systems. And Bill could attest to reviewing dozens of schools that don't meet their design criteria because their operations have been compromised. So retro commission, as Charles said, is really, really critical. Is the building performing the way it's designed, the way it could be? How could it perform better? So that's really important concepts, I think, that are necessary going forward with buildings of different year stock as well. So did anybody else have any thoughts?
Yeah, I'll comment on your carbon dioxide comments. Joe, I often bring a carbon dioxide, or sometimes bring a carbon dioxide monitor into my classroom as I'm teaching class, and just to show the cadets the impact. It's first thing in the morning, and the first one shows up, and I say, "Oh, look, it's about 500 parts per million," and then the other, 15 of them come in, and we see the huge spike, especially since they had to walk up 6 flights of stairs to get there. And so then there's always this big spike, and then we reach a steady state, and then we can open a door and show that the carbon dioxide level goes down, and it's a great experiment. But I really like your simple approach, Joe, because we can do all the modeling that we want, but really it depends on the particular conditions in a particular place. And if you keep the carbon dioxide below 700-800 parts per million, generally it's an indicator of healthy air. So I think it's a very simple, straightforward approach that's easy to implement and cheap too. Those monitors nowadays are pretty inexpensive.
Yeah, thank you, sir. That's a good point. One of the things I learned from my carbon dioxide monitor is if you're in a car and your windows are closed and you're in there for 15 minutes, all of a sudden you need to open up the window. And most people don't realize that. They just get a little tired and sleepy. Open up the windows. So I guess that concludes well ahead of time. I mean, we had fantastic speed going through this hour and a half. Medea, I'll turn it over to you.
Great. Thank you, Joe. Thank you to all our panelists. Thank you to everyone who came today. A lot of information packed into a short webinar, so thank you so much. And I will follow up with all of the attendees with an email. If you're seeking PDH credit, you'll look for the email because it'll have a link to the survey and you need to answer the survey. And if you're looking for GBCI or AIA credit, we will report that on your behalf as long as I have your GBCI and or AIA numbers. And if you aren't sure, just shoot me an email, and you should have my email address already because I sent out a reminder for today. So I will send links on our upcoming events. I put a link in the chat to the article that provides links to our previous sessions, and this session is being recorded and we will put this on YouTube as well. Thank you again, everyone. Look for our next session on March 8th. They're all on Wednesdays at noon. And then we have April and May, and then look out for our October summit, which should be a hybrid event. And thank you again. Shoot me an email if you need anything. Thanks to everybody.
Thank you, everybody.
Thanks very much.
Thank you.